Alright, so in this video I'm going to introduce you to differential scanning calorimetry and talk about how it can be used to understand protein folding thermodynamics. So first we'll go over what a differential scanning calorimeter is. And here we have a schematic of one right here, and it is made up of a set of heating elements and a temperature monitor. And these heating elements are applied to two different solutions, B and A. One of your solutions is a solution that is just a buffer, and the other is one that contains a protein of interest and the same buffer. And so what this does is it scans the temperature of both of these solutions up. And as it does this, it is constantly using its monitor to monitor the temperatures. And as it scans the temperatures up, it makes sure to keep both of them at the same exact temperature. So they're both kept constant. And if these two solutions have different heat capacities, this will require different amounts of heat input into them. And so what this instrument does is it actually measures two parameters for each solution. It measures the heat flow in, which is quantized by dq over a certain period of time, and then it monitors the temperature change, which, since both of them are being kept at the same temperature, is the same across both solutions. So what you can do is you can determine the heat capacity of one of these solutions by dividing the heat flow. Let's do the heat capacity of B. You could divide the heat flow into B by the change in temperature with respect to time. And that gives you this amount of heat. It gives you the amount of heat required to change 1 unit of temperature, which is heat capacity. And similarly, you can do that for the other solution, A, which is the one with your protein of interest. And what you do, if you want to actually see what the heat capacity of the protein is you compare the two. Because the solution is also taking up a bunch of heat, but that is not what we're interested in. So the heat capacity of the protein is actually the heat capacity of the A solution, which has the protein in it, minus the heat capacity of the B solution. And this is the source of the name differential, because it's actually calculating the difference in the two heat capacities of the solutions. And an interesting point about this is that this allows you to include it includes solvent effects, which are very important to proteins because they are always in a solvent in biological systems. So now let's talk about the type of data that comes out of one of these instruments. So here on the left is a typical differential scanning calorimeter curve for a protein. Note that on the left, on the y-axis, we have the heat capacity of the protein, which has been derived from subtracting two solutions' heat capacities. And what we end up getting is this big curve that has this hump in it right around the melting temperature of the protein. And then it settles back down to a higher heat capacity. So the source of this big hump here is the cooperativity of protein folding and unfolding. And that gives you this big hump because as you start to unfold just a few residues from their native conformations, the whole protein sort of falls apart. So you get this huge change in the conformation, which requires all this uptake of energy as you're breaking these weak bonds like hydrogen bonds and ion pair interactions. What you would normally get, or what you would expect to get if there was no cooperativity in protein folding, is a heat capacity curve like this. Also assuming that there is a change in heat capacity between the unfolded and the folded states. So right here we have the unfolded, and here is the folded heat capacity. And then right in the middle you get this nice smooth change between them as the two fractions of folded and unfolded trade off. And that's given. You can get this curve by plotting this equation here. So if we were to insert the curve without cooperativity in unfolding and folding, it would look sort of like this. And so now we have this huge area above it that is actually very interesting, because this area is the enthalpy change of unfolding. So you integrate over the heat capacities, which is the y-axis here, and you end up getting the enthalpy change of unfolding. And it's important to note that this is at the melting temperature, not across the whole protein. And some other good parameters that you get are the heat capacity of the folded protein, which I'll denote with a superscript F, and then the heat capacity of the unfolded protein. And this other parameter is derived from these two, this delta Cp, which is the change in heat capacity between folded and unfolded states, and that is simply the heat capacity unfolded, which is always higher, that subtracted by the heat capacity of the folded protein. So this is always positive here. And other things you get from this is the melting temperature of the protein, when half of the protein species are folded and the other half is unfolded. That is the top of this heat capacity hump. And since we've gotten the delta H of unfolding at the melting temperature, we can tie it to the entropy change of unfolding at the melting temperature through Gibbs free energy. So I'll explain that real quick. So let's imagine the reaction of the protein going from folded to unfolded. This is the unfolding portion of it. And at the melting temperature, we know that the concentration of folded species is equal to the concentration of unfolded species. And so that tells us that the K, which is the concentration of unfolded over folded, is equal to 1. And plugging that into the Gibbs free energy equation, we know that the Gibbs free energy at equilibrium here will be 0. So with that, we can get that as 0, the Gibbs free energy, equals the delta H unfold at the melting temperature minus the melting temperature, delta S unfold. And then we get the relationship between the two, and we can find out that the entropy change of unfolding at the melting temperature, important, is equal to the enthalpy change of unfolding, which we got from the differential scanning calorimetry experiment, divided by the Tm. So this is also at Tm. So this is a good equation, but it's really important to note that this is at the melting temperature. So it's only at one particular point. So you can't actually use this equation to calculate entropy changes at different temperatures because of the temperature dependence of entropy change and enthalpy change. So, since there's a temperature dependence of the heat capacity and thus the entropy change, you can't use your typical Van Hoff analysis. So temperature dependence implies you can't use Van Hoff. But what you can do is you can leverage the fact that these delta H's and delta S are all state functions, and you can use thermodynamic cycles to adjust these equations for different temperatures. And that is in box 10.3, I believe, in the book. Oh, that is actually box 10.2. And once you go through the math, you get these adjusted equations for entropy change and enthalpy change at any temperature. So these are for any temperature. And you input into them the enthalpy and entropy changes at the melting temperature, and also input this parameter of the change in heat capacity between the folded and unfolded. So this whole section right here is the temperature dependence adjustment for both of these equations. So you can plug the enthalpy change and entropy change into our familiar equation, delta G equals delta H minus T delta S. And then you can get this really cool equation for the Gibbs free energy change of unfolding a protein at any temperature. So this is really useful because you want to know the stability of your protein at whatever temperature. And you can note here that if we were to take out these terms here, which are the temperature adjustment terms that I showed you before, you would just get the normal delta G equals delta H minus T delta S. So if there is no change in the heat capacity between the folded and unfolded states of the protein, then the delta H and delta S are temperature independent, and you'd be able to use this equation and be able to use the Van Hoff analysis like normal. But that is not the case. So what you end up getting is this temperature dependence, and like I said, if it was temperature independent, you would get a delta G relationship with temperature that looked like this, just because it scales with temperature directly. But instead, you get this red line. And that has some interesting implications, because if you can see that as parabolic. If you extend this red line backwards, you can see that it actually crosses once again here, and this is the delta G equals 0. So this is equivalent to the melting temperature, where one half of the protein is folded and the other half is unfolded. And this point here, which is at a colder temperature than the melting temperature, is called the cold denaturation point, and it is entirely dependent on the fact that there's temperature dependence on delta H and delta S. And so what you can get is a second point where proteins unfold. And this top one is the familiar one, where it's the hot denaturation of proteins, where you heat them up so much that they just unfold.